So there are 12 total sections in chapter 12. And as you can see, if you look over on the homework board where yesterday's homework would have been, tells you the chapter 12 mastery will be next Wednesday. That is because we will do 12:9 today, 12:10 tomorrow, 12:11 on Friday, 12:12 on Monday, and have Tuesday to wrap up anything we need. It'll kind of be a work day, review day sort of thing. And then Wednesday, I'm gone. I have to be at the WEC all day for another math calibration meeting. So, figured you guys can at least start the test then. If you have any issues, then on Thursday when I'm back, we can deal with that stuff. Greg?
It's an open note test, right?
Probably, but I'll need to see your notes beforehand then, because I won't be here to monitor what you actually have, so that's the only thing that makes me nervous about that.
What do you think we would do? Write
Cheat.
test answers.
Write cheats on
Oh, you mean so you can
When
see
content is difficult, good people make bad choices. I don't think any one of you would like just say, oh, I think I'm going to cheat today, but if you get stressed out and you're like, but that's always the concern.
You ever say that you're going to cheat?
So when I look at this pattern, and we see lots of different puzzles and things like this throughout the world, because people like models like this, and especially when they get very difficult, especially when they're three-dimensional. So we're looking at a two-dimensional model that, as you can tell, keeps adding a new row of triangles on the bottom, shifting everything up. So from stage 1 to stage 2, we added a row of 3 triangles on the bottom. From stage 2 to stage 3, how many did we add there?
5.
Yeah, the bottom row now has to be 5, so we add 5 more. How many do you think we'll need to add
7.
in the next row? 7? 17?
30.
Yeah, I think that would be a lot. How can you make that prediction?
Because I just guessed.
What are we really doing?
Oh, I got it.
Yeah?
Wait. No, that only worked for
Because if this has 1, 2, 3, 4, 5 on the bottom, 3 next one up, and 1 next one there. Yeah. Do you know it now, Greg?
Okay, you copy the bottom row and just add 2 to the end.
So we can essentially take the previous shape. The bottom row can go on the bottom, but we can't just copy it. We have to copy it and flip it over.
Yeah.
So now this would look like that with your triangles. 1, 2, 3, 4, 5. And then I'd have to add 1 out here and 1 out here. Every new row is going to have to add 2 triangles more than the previous bottom row. So to get to stage, because this is stage 4, to get to stage 5, how many would we have to add? 9 more, because the bottom row is going to be 9. So if we were to try to think about stage 9, I don't have enough space on the smartboard to write it out. Emily, you've had your hand up.
Yeah, okay, so this could be terribly wrong, but I...
Don't preface statements with that. It sets up people's minds with a preconceived notion.
Yeah, that's the point.
Okay.
Okay, so I was looking at it and I wrote some of the numbers down and it looks like just like whatever stage it's at, it's just that squared for how many triangles it is, because you keep on adding things. Like,
Well, let's play out that hypothesis. Stage 1, if we had 1 squared, we have 1 triangle. Stage 2, we have 2 squared, we have 4 triangles. Seems to work. Stage 3, we would have 3 squared. 5, 3, and 1 gives me 9 triangles. Stage 4, if we did 4 squared, we'd have 16, which we said that this portion up here was the 9 that we already had, plus another 7. That would give me 16. If we add 9 more to that, that would give me 25 in my next stage. If we add 11 more to it, that'll give me 36. What?
Pascal's triangle is
Well, Pascal's triangle has like numbers associated with it.
So this is somewhat open.
It's a model similar to Pascal's triangle.
It's
Look it up. It's really cool.
the famous triangle.
So, if we're going to continue this pattern, and Emily's hypothesis holds true, then it should just be whatever my stage is squared. So in stage 9, what would you anticipate?
81.
81, right? Now, how could I graph if I had like my x-axis being stage
Would that be
and my y-axis being number of triangles? They really just like flip a coin between you guys, Leon.
Squared.
Huh?
Y equals x squared.
Well, so that's the equation of it, but what would the graph look like?
It'd be a parabola.
No, it
No,
wouldn't.
it'd be a straight line.
It would not be a straight line.
What?
Kale?
It'd be like an exponential equation.
Say it louder.
It'd be like this. It's an exponential equation.
It would be an exponential because in stage 0, how many triangles do I have?
Who knows?
Stage 0. Before we start, we have 0. What about stage -1? There is no stage -1. You can't go back in time.
There's -1.
So when we talk about exponential graphs deal with the fact that we want to keep getting bigger and bigger and bigger. Every step we take is bigger than the step before, and it will keep going like this forever. So if you think about what stage 16 would be here, that'd be a huge triangle. Stage 20 would be 400 triangles. Stage 30 would be 900 triangles. It would get really, really big really fast.
What about stage?
That's when we talk about the difference between the 3 main types of graphs that we have. We have linear graphs that you guys dealt with in 7th and 8th grade math. Straight lines. What is a characteristic of a linear graph? We have 2 main characteristics that we talked about when we learned them.
It has a constant.
Well, okay, it's a straight. That's what linear means. What?
Never mind.
It's straight.
Gonna
Right.
say it has a constant speed.
Because it doesn't end.
Continuous. Yes, I mean sometimes depending on the constraints on the situation, we would only look at a certain portion, a certain domain. What does the M do here?
Slope.
Tells us the slope. So a linear graph has a slope that is constant.
That's what you literally said.
I
So
said
why didn't
number
you
of
say it
I
out
said
loud?
number- I don't know.
Then what's the B?
Y-intercept.
A y-intercept. So those are the 2 main characteristics of your linear graphs. It's got a constant slope and a y-intercept. What about a quadratic?
It's curvy.
Curvy. That's not even a good word we want to use here. Symmetric. This graph is going to be symmetric. You could also say it has a line of symmetry. Jacob?
The slope is always changing.
So the slope is not constant, so we have a continuously decreasing or continuously increasing slope. So we don't actually really even talk about slope because it's constantly changing here. I mean, we could, in any one instant, we could talk about the slope, but if we talk about a portion, there's no way to deal with it. Now you could have a line tangent to a point and figure out that line's slope. So if I drew a line that touches at the 0, that would be our tangent line. And we could find that slope, but that only counts for the instantaneous moment that it touches. So it's metric. We can either find zeros or solutions. We'll either have 0, 1, or 2 solutions. If this is a real situation that can happen, there has to be at least 1 solution. It's got it's going to have either a maximum or a minimum, but really we can talk about that as the vertex. It's either got a lowest point or a highest point that maxes or minimizes what values are possible. Now what about an exponential?
Y-intercept.
Yeah, so it will, we, rather than saying never crosses the x-axis because depending on the situation, it might. What we say is it has an asymptote, or A-S-Y, asymptote. So, an exponential graph is going to have an asymptote, which is a line that it can never cross. Here, the exponential shown to us, the asymptote is the x-axis, Because it will get, as we go left, it'll get closer and closer and closer and closer and closer and closer and closer to the line, but never touch it. It's the idea, if you haven't heard this model, it's the idea
Of the arrow.
that I am X distance from the door right now.
Oh, half of that.
I can walk halfway to the door.
What third?
I can then again walk halfway to the door. I can then again walk halfway to the door, and if I continue to walk halfway to the door, and halfway to the door, and halfway to the door, if I always go half of the distance there, I'm gonna get really, 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 really close, but I'm never actually gonna reach the door.
That's
why
why
I
I
You did. Yeah. The doorway. So yeah, so what you guys have heard is the whole I'm not touching you scenario of siblings, where I am X distance from Kale. My fist is now half the distance to his face. My fist is now half of that distance to his face. My fist is now half of that distance to his face. And you can get closer and closer and closer and closer. Baylor, get out of here. But you'll never actually. Yeah.
I feel bad, those are hits.
Huh?
The Altoid box.
Where'd you find it?
They found it back there and they just took all the gum and chewed it.
So here's what you guys need to do. You guys need to buy gum and bring it to give to Baylor tomorrow. Because you found something that wasn't yours. I didn't realize what was going on. I just thought one of you guys brought that and you were sharing it. This goes back to the very elementary rule. Who knows what I'm going to say?
Sharing is
If
caring.
If it's not yours, don't touch it. No, I agree. Sharing is caring. But he did not choose to share that with you. Right? So Greg, what if I went to your locker, pulled out like your lunch, and ate the whole thing? You'd be pretty annoyed, right?
Yeah.
So don't touch something that isn't yours.
Ha, I did touch it.
You guys need to figure out who's gonna buy the gum and bring it for him. Understood?
Hey, Leon.
Hey, are we understood? Because otherwise I report this as theft. And I don't want to do that. Are we cool? Gonna make this happen tomorrow? Yeah?
Why are you looking at me?
Because you guys were all in the group. My eyes are shifting. When I look at you, you notice I look at you. Who's getting it together? Who's buying it? And then whoever's not buying it is getting it. So you guys all need, it's like literally a quarter from each of you. Will be fine. Alright, has an asymptote. It is, an exponential is either always increasingly increasing, or increasingly decreasing. It's always getting more positive than it was before or more negative than it was before. Because you can have exponential models that go negative, but it's always changing how big the steps are.
Hey, oh yeah, for Michael Cortez for a wholesale price of 75 cents. Just saying. What?
Alright, so when we have a list of points given to us, if we plot them on a graph, it gets pretty easy to see what type of graph it's going to be. So if we take these 5 points that we have here, jot them down here real quick. So 1, 3.
Mr. Hudson?
Yeah?
Seeing that there's 2 0 points, can't you say this coming, like, since it's y, can you say it's going back up? Since it's
So,
going back, then it's a quadratic function.
1, 3, 0, 0. Very astute observation from Mr. Stravler. We have 2 0 y values. Negative 3, 3. Negative 1, negative 1. And negative 2, 0. Yeah, we see that the appropriate model for this would be a quadratic. Any questions on that? Please make sure you get that on your paper. Try number B on your own.
I did first.
You did B first.
Wait, I got this guy.
No.
No, they'll call me.
It's called ladies first, and that's why I did it.
Wait, you just call yourself a lady.
Yeah, but I'm still gonna get ladies first.
I mean, don't you ever listen to Aerosmith? Dude looks like a lady.
Ooh.
If you don't know what I'm talking about, you need to get some musical education.
Oh, Aerosmith came out on the bus yesterday, or Monday to wrestling. That was on. It was sweet. Okay.
Now, for the just for the fun of debate, Wyatt's hand was up first. Let's see what Wyatt has to say, and let's see if you agree, Leah. Wyatt, what do you think?
Exponential.
Now, why do you say that?
Because it never touches the x.
It never touches or crosses the x-axis. It is decreasing, but not at a constant rate. Because if I look at my slope from here to here, I have -2 over 1. If I look at my slope here to here, I have -1 over 1. I have -1/2 over 1. How else do I identify that it's exponential and not parabolic? Jacob?
Like the amount, it's getting halved every single time.
-2, -1, -1/2. The change in the vertical change. Listen to what I'm actually saying. The change in the vertical change is halving. Or, if we're going up, what should the change in the vertical change be doing? Doubling. So, whether you're exponentially decreasing or exponentially increasing, it always deals with the ratio 2 to 1 or 1 to 2, depending on which way you go. So this would be exponential, and it's exponentially decreasing.
Do we have to graph this on our homework? If we have to.
I forget exactly what it asks you to do. I think it gives you, again, it just gives you points and it says which model would be appropriate.
I'm not looking at it. You can kind of
All right,
tell.
Leah, did you go ahead and do C yet?
No.
Oh, I thought when I picked Wyatt, you would have flipped to the back and done C.
I should have thought of that.
I'm sorry.
Skid.
You got it.
I called it, got it.
Okay, got dibs.
I called it, John.
So,
So my hand up first. I had my hand up before we came.
Hey guys, I don't know what's going on. It's kind of creepy.
Put it in the wrong place.
Huh?
Put
Negative.
-1, negative.
It's -2.
Ah, good catch. Thank you.
I think I know what that is.
So Leah, now that you have these points graphed, what do you think?
Linear.
Linear? How do you know?
Because it just goes straight out.
So I agree, but depending on what window of a parabolic graph you're looking at, they can sometimes look like this if you only have 3 or 4 points. So how to verify is you say my slope here is a +1, my slope here is a +1, my slope here is a +1, my change in my change is consistent. We know it's linear. So that's just how you verify it. So totally right, but you want to make sure that you check it because there are instances where they give you a very small portion of the parabola. Like think about if I drew a parabola on this graph and then only had you look at that window of the parabola or this window of the parabola, like it will look linear given a certain snapshot. So you just got to be careful that you think about what is the change in my change, the change in my slope, essentially. Got it. Greg, while I plot these points, what type of graph do you think is appropriate here?
I think it's exponential.
Oh.
You think it's exponential. Let's evaluate it. What's my change from my furthest left point to my next point? Yeah, it goes up half and runs 1, so half over 1 would just be a half. What's my next change? 1. My next change, my changes are doubling. Now this is why we didn't say it never crosses the x for an exponential. It has an asymptote somewhere, down here, approximate area. We don't know exactly where it is. We could compute where it is if we need to. But it will be an exponential. That make sense? Okay. This is why I was hoping we could just survive the middle part of the chapter and get to this section.
Yeah,
So if we go look at problem 2.
In this problem, you will choose a model using differences or ratios. Part A.
So if you don't want to graph it, Sweet, thank you for reminding me. If you don't want to graph it, we look at the change in the change. So we can evaluate what is the change in each of my x's. We like it when my x changes by 1, because then my y change just tells me what the slope is. If my x changes more than 1, I have to do the division. So since all my x changes are 1, my y changes are my slope. So my slope from my first to second point, -4, second to third, -4, third to fourth, they're all the same slope. So what, does that tell me since they have a common difference? Traveler? It's going to be linear, which I mean is on your paper, because the change in the change is consistent. But, Jacob? Sorry, went too far. Go back to A. Go back to A. There we go. So, this is what we really mean when I keep saying the change in the change. Notice that the change of your y is -4, but the change in the change is 0. So we call that consistent, really, that the slope is consistent. But when we move on, and the changes are not all the same, so my x changes are still 1, which is great, but my y changes change. My first one goes down by 1/4, my next one goes down by 0.75, my next one goes down by 1.25, my next one goes down by 1.75, so I know this is not linear. And this is where the difference between quadratic and exponential really can be found. What is the change in the change? So my change in my change from 1/4 negative to 3/4 negative is just 1/2. My change in my change from 0.75 to 1.25 is 1/2. My change in my change from 1.25 to -0.5 is still 1/2. So the change in the change is consistent, which tells me, Jacob. Yeah, I'm assuming that you knew that before.
I also have something to say about recording itself, because so I tried to go back and watch some of the videos, but you never stopped the video and you never muted the computer. So
Yeah,
even though
I'm
the
still trying to
speaker-
figure out how to mute the video.
I think you just have to turn your sound off.
No, like
No.
on it picks up through the computer before the speaker. So I wonder if I kill this sound, if that'll do it. But I don't think so. I think it picks it up before it even
Yeah,
processes.
because I couldn't hear what you were saying.
Yeah. So let's try that one then. Like I'll let the next video play and then we'll see if it picks up the audio or not. So when we really kind of call this, some people call this like the level 2 change, because this is originally looking at my delta y. And then this is looking at my change in the change of y. So it's like the change of the change. You guys know the triangle means change in, delta.
Yeah.
Greek symbol delta means change in. All right, so figure this out. I like to first. Do I need to separate you guys really?
No.
Because you keep trying to poke at me.
No.
I like to first set up an XY table. Please stop with the Adele.
Adele.
It gets stuck in my head every day because somebody is singing it.
Yeah.
Sure, stop with
I
Adele
went to the
computer
beach-
too.
I went to the beach and I lost my in the water. Boy.
What?
So we look at level 1. We look at the delta y. My delta y's are not consistent, so that tells me it's not linear.
Oh, I know what it is.
So then we move on. Look at the change in the change. Here that's
Why
a
would we
half.
need to do that?
Here that's a 1.
Oh.
Because if my change in my change is consistent, like it was back in, which was it? B. that told me it was quadratic. But here my change in my change is not the same. So this would be exponential.
I hope the homework's this easy.
So what you can really do is just figure out what they aren't. If level 1 is consistent, it's linear. But if not, it's not. If level 2 is consistent, it's quadratic. So if it's not, it's not. And at that point, you see, well, it has to be exponential. There's a parody of that, like from a teacher singing about how they don't get any snow days in their district.
You want to hear a joke?
All right, so now we can see if this video
In this problem, you will model real-world data. The data at the right give the value of a used car over time. Which type of function best models the data? Write an equation to model the data.
All right, so here, when we start looking at, I don't know where 3 went to. Part 3 got chopped out of your notes somehow. All right, regardless, we've got our XY table. My X's are all changing by 1. When I look at my Y changing, so for some reason your notes say that this is problem 4, but it's actually problem 3. So this is in your notes. When I look at the change in the change, or sorry, first just the change. 12,575 to 11,065. Thanks. I was waiting for your drum solo to be over. So when we look at this data, my changes in X are all consistent. My changes in Y, when I look at them, now why do you see off to the side of your graph, why do they have that 0.88? Like, when we first look at these, hopefully it gives us, how are they finding these? What are these values actually representative of?
Is that like the percentage kind of? Like 100 or 11,065 is like 88%.
Yeah, it's the ratio. So we're looking for what is the ratio between them. So why do you think finding that ratio would be beneficial? Yeah.
Isn't it like finding slope basically? To see if it's constant.
Kind of.
Well, it's like to see if it's constant.
Well, so we could look at the delta y, not the ratio, but if we look at the delta y, we'll see it's not consistent. This is not a linear graph. So when we see that it's not linear, Jacob, I can explain it, or I want to see what you have to say.
Because, if we go back to the first graph where the ratio was 1/2 or 2, then, so they had a common ratio, and that's why it was labeled as exponential, but because they don't have a common ratio here, then it can't be exponential.
Okay, so graph curves does not look quadratic. It may be exponential. You see the thought process in number 1. We're thinking it may be exponential. So then as we keep going, though, we really want to set up an equation to represent this. And what we're doing, and these are all very close. Those are approximate values. So when we look at those, they're all really close to 0.88. If we average them out, it's going to be 0.88 because we have one below and one above. So that is actually the base of my exponential. So this is actually, well, can be roughly modeled by an exponential. Now, not all sets of data can be perfectly modeled with a linear or quadratic or exponential. Sometimes it's just not perfect because it's real world data. So that's why we have to average the ratios here to find the base of the exponential. Where does my 12,575 come from? It's like your y-intercept. It's your starting point. So we start here, and to move to the next point, we just apply 88% or 88 hundredths, or however you want to say it, to the x power, because if it's the second year, the 88% will have happened twice. So we square it and then multiply it, or we could do times 0.88 and then times 0.88 again. When you multiply something by itself, it's just squaring. I'm going to capture that really quick.
I have a question.
Yeah.
In a real world like situation, wouldn't it be like a parabolic or parabolic?
So if it was parabolic, that would say that the value of the car is going to come back up.
Yeah.
So when you think about a car's depreciation, you know what depreciation is? When Robert buys a new video game for $60, as soon as he opens the case, the value of the game has depreciated. Now the game, the disc, the content has not changed. When I buy a car and I get home in my driveway, I just bought the car, brand new, got home, I drove it like 20 miles. Nothing's really changed on the car, but it's now worth thousands of dollars less. Depreciation is the decreasing of value based off use, and it's skewed. It's very skewed. Because when you buy a brand new car, and this is why some people, myself included, will say that brand new cars are a bad investment. Sure, they're brand new, but as soon as you buy it, as soon as it's yours and you are the first owner, it's now been owned. It's now been used. It's no longer new, and it's worth thousands of dollars less. So the initial depreciation in a car is pretty big, but after that it starts to slow down, and there's going to be a point where it kind of stops losing value. My buddy just bought a new car last week, bought a new Nissan Rogue. He sold his Toyota Camry, or Toyota, yeah, it was a Camry. It was an 02 Camry. He's like, man, what can I get for this? Like $1,500, maybe $2,000. I was like, dude, you can probably get $2,500, maybe $3,000. He took it to CarMax. They gave him $3,000 for it. Even though it's old, even though it's got a bunch of miles, it's still a car in good functioning order. It does not keep decreasing down to zero unless the car gets like damaged or something like that. So these graphs, the asymptote that we're going to see here is really like that minimum value that the car is going to be worth, or the minimum, like whatever the situation we're talking about. So trying to make it a little realistic for you guys. If we have annual income of a small theater company, so do you think this theater is improving or like getting worse? Improving, right? Because the annual income, how much they're making every year, is increasing. Now, if we look at the delta y, I can do some quick differences here. 730 minus the 254, that's 476.
485, 480, 480.
Are they constant? No, they're close, but they're not constant. So what we do here, it's probably going to be easier for me to just show it. Come on. So we could go ahead and put the data on a graph. Now this looks pretty close to linear.
But it's not.
Well, that's the problem with real world data. If we look at what's going on here and we try to model a line, well, let's think about an exponential. Exponential is going to start somewhere and keep going up and get faster and faster and faster, or keep going down. Well, that curve doesn't look right. It would start almost straight and keep going down. So I don't think either of those would really work. Parabolic would say it's going to go down and come back up. So even though this is not a perfect linear graph, we can approximately model it with a line that would go through most of these. Do you guys remember where we do the line of best fit? Did that back in, I think, Math 8 and Math 1. So if we look for a line of best fit here and try to model that change, well, those changes that Ben gave me, where they were like 476, 485, 480, 480, if we average all those out, we'll get 480, right? I mean, 476, 485, they're both, we'd get like just over 480 when we average out, like literally just over 480. So we actually do approximate it with a linear model. Even though it's not perfect, it's real world data. We need to model it the best we can. So it may not perfectly model each and every point, but approximately that takes care of our data.
480.25.
Yeah, 480 and a quarter. So if we really wanted to be as exact as possible, we could write this out. Y equals 480.25x plus my initial from that year 0. What do you mean? With the ratio?
Yep.
No, because when we think about this situation, it's not going to be an exponential situation. There's no way that a theater can keep making more and more and more, like more of a difference than the year before, and more of a difference than that year before, and then more, like it's just not feasible. This is where you have to like take your math knowledge and apply real world thinking, like street sense. A theater, that's not going to happen. A car is going to depreciate, and then level off. A population of animals, if they are repopulating, that could be described as an exponential unless something else is going on. Because if you think about how an animal population increases, as you have more animals to repopulate, you'll have more offspring. Every single year, you'll have more and more and more. Yeah.
Will a theater, like, once it gets better, like, more people will come, and therefore they're going to get a higher, like, and then they're going to keep on making it better, but...
So what sort of restrictions would come into play if we were thinking about why this wouldn't be exponential? Like, how does a theater make its money, Greg?
Oh, I was gonna say why then. Like,
Okay.
because we don't have that much money in the world.
Yeah, so eventually the model just can't happen because people only have so much money.
Also, to make the show better, they'd probably need more costumes, more sets.
Yeah, as they make more, they're gonna spend more. So when we looked at that, we were only looking at annual income, but we don't know exactly if that's gross or net. Gross would be before expenses, net would be what they actually profit. Ben?
You asked how they make their money?
Yeah.
Off the concession stand.
That and tickets, right?
Mostly
So
off
they,
the concession stand.
yeah, they only have so many seats. They can only sell so many tickets. They can only sell so much popcorn or whatever because there's limiting factors. The fact that it's a building with a finite size with finite seats, they're going. That's why. Yeah, that's why this cannot be an exponential model. So you got to think about what we're really talking about. Have you guys ever heard about carbon dating? Carbon dating? Carbon dating works on an exponential model. Anyone know how to explain it?
Not really.
Why can we carbon date stuff? Like a fossil, we can carbon date it.
C14.
What? Why?
Because it decreases at a constant rate.
It has a half-life. We know what the half-life of carbon is. So when there's carbon inside of something, we can take how much is left and work the problem backwards to say how old is this based off the amount of remaining carbon. Because I forget what the half-life span is, but it's like every so many hundred or so many thousand years, it will half itself.
Is that why we don't have how long?
Yeah, that's how we have the dates for fossils. That's how we know how old
It's kind of
things
the
are.
same thing as the mathematical function. Because it gets the half of itself and then it halves itself again.
Yeah,
But you can
exactly.
never exactly get rid of it because it keeps on going.
Yeah.
But when nuclear just turns out that since they release C14 needed it to
It depends on heat down stuff is. Like, and it would depend on if it's like
You gotta
exterior
say,
or
well,
interior.
you can't mathematically.
So that is a good question though, whether or not that would affect it. It should be right over there.
I don't know where it is.
Oh, they're still not down in the stack.
They can't mathematically put together a new.
There we go. There we go, Robert. All right, guys, grab one of these before you get out of here. Yeah, because it makes it easier to hand out. Oh, yeah. There's only 18 problems. Don't hate me.
Jacob,
else needs it?
I need that.
I used to trust you. Who else needs it? Anybody?
You can't mathematically